Motion problems. Uniform motion is when something is moving at a constant speed. And as long as something's moving at a constant speed, we have this equation that we can write that relates speed, distance, and time. And so speed is usually written as S or V. If you've taken Physics 11, you'll see it usually written as V, which actually stands for velocity. But we can also use S. So I'll use S in this math context because we're not as interested in physicists as being so exact about our words. So what we'll say is that the speed of something is equal to the distance that it travels in the time that it takes to travel at that distance. So speed is equal to distance divided by time. And this is a really powerful equation because it relates three very important measurements together: speed, distance, and time. And we can also rearrange this equation in many different ways. So speed equals distance times time. What I'll do is multiply each side by time and eliminate it from the right-hand side and find that I get this equation that distance is equal to speed times time. So there's a really common rearrangement of the formula. So if you go 50 kilometers an hour, that's your speed, times time for, say, 3 hours. 50 times 3 is 150 kilometers. So you can use this equation to solve for distances really easily. Another rearrangement we can do is if we start from d is equal to s times t and divide each side by s, then we get an equation for t. The time is equal to distance divided by speed. And this is a really great equation when when you need to know how long it will take you to get somewhere. So if you need to go 300 kilometers to drive up. So I'm here in Victoria. If I want to drive up island, roughly 300 kilometers, and I know that on average I drive 80 kilometers an hour along the highway, the distance of 300 kilometers divided by 80 tells me that the trip would take 3.75 hours. So it's a great equation for estimating the amount of time it will take for you to get somewhere. Now, as you can see, two of these equations involve fractions. And so if we're doing some speed, distance, time equations, we're often going to have to solve some rational equations that are involved, that have fractions in them. So we're going to be applying our rational equation solving skills for these types of problems now. So very quickly, I want to talk about getting sped up or slowed down, because this is going to be a really important part of these speed, distance, time problems, what we call motion problems. And so there's a couple of vocabulary things that I want to talk about. I'm going to draw a really terrible airplane. There's my terrible airplane. I'll give it an engine. When you have an airplane that's getting pushed from behind by the wind, we call this a tailwind. And it speeds the airplane up. And if you've done a lot of flying, you'll find that flying one direction, like flying across the country, is a little bit faster commonly than flying in the other direction. And that's because there's a common wind that might blow east to west or west to east that will speed you up if you're flying with the tailwind pushing you along. So if a plane goes x speed, then with the tailwind, it will go x plus the additional tailwind speed. And the same thing can happen if you fly against the wind. So now I'll just again draw my terrible airplane. Oh, it's getting a lot worse. But now say I fly into the wind. So the wind is pushing against you. This happens a lot when you go biking. This is what we call a headwind. And the headwind slows you down. So if you go x speed, you have to subtract the headwind speed. So if you're flying at, oh, I don't even know how fast airplanes fly at the moment, but let's say biking. If you're biking at 20 kilometers an hour, and then you bike into a 5 kilometer per hour headwind, you might get slowed down to 15 kilometers per hour in the most simple case. And then one other situation where we see this a lot is in the water. So if you're in, say, a river, which is moving some direction, and you're paddling, or you're a boat, any kind of boat that has an engine, so your speed would normally be x, but let's say you're going in the direction of the water, we would call this going downstream. And again, you get sped up. So you go x, whatever speed you would have in still water. So this would be x speed in still water, like on a lake. You'd get boosted by the downstream speed, the speed of the water downstream. And likewise, if you're in a river that's flowing against you, we call this going upstream. And so your speed would really be your still water speed subtract the speed of the water pushing against you. So subtract upstream speed. So we're going to see some examples now where we solve problems involving our speed and whether we're going with or against some kind of medium like the air or the water. So now we're going to go into our first example here. An airplane can fly 300 kilometers into a 30 kilometer per hour headwind. So that would be against the wind. And it can do it in the same amount of time. That's going to be important, in the same amount of time that it takes to fly 400 kilometers with a 30 kilometer per hour tailwind. And we want to know what is the speed of the airplane in no wind. It's always really important in these problems to identify what you're trying to find. The speed of the airplane in no wind, I'm going to call that x. That's our unknown, what we want to solve for. So what we know is that the speed of the airplane going into the headwind, I'll call that s with a little subscript head, that speed is x, which we don't know, minus 30 kilometers per hour. However fast it's going, subtract away 30 kilometers per hour. And we can do the same for the tailwind. The tailwind s tail, the speed with the tailwind is x, which is how fast it would go without any wind, plus 30 kilometers per hour. Now, how am I going to relate? The other thing we have is I should write the distance. So the distance with the headwind, it can go 300 kilometers. And the distance with the tailwind, it can go 400 kilometers. It can go further because it's traveling faster. Now, how am I going to connect these things in order to solve for the speed of the airplane with no wind? And the key is what I highlighted in yellow, that it takes the same amount of flying time to accomplish this. So what I can do is I can say that the time flying in the headwind is equal, so I'll write t head. The time flying in the headwind is the same as the time flying with a tailwind. And now I've got my equations for speed, distance, and time that we talked about earlier. So I can see that my equation that relates speed, distance, and time, I can get that the time is equal to, so the time for the head is equal to the distance divided by the speed. So the distance into the headwind over the speed into the headwind. And I want to replace time because all I know is that the times are equal, but I have no values for the time and I'm not asked to solve for it. So if I replace the times with the distance into the headwind and the distance into the tailwind divided by the speeds, now I have an equation which I can replace with all my values and solve. So by putting in my values, the distance into the headwind is 300, the speed into the headwind is that unknown x minus 30 kilometers per hour, and the distance into the tailwind is 400 over x plus 30 kilometers per hour. I've now set up an equation that relates my speeds and my distances using the fact that the times are equal to set up a rational equation that I can solve. And how would we solve this rational equation? The same way we'd solved them previously. We're going to multiply each side by the smallest thing that we need to eliminate the denominators. So I'll multiply each side by x plus 30 times x minus 30. And on this side, I need a little extra room. X plus 30 times x minus 30. And cancel anything that can cancel. And I'm left with 300 times x plus 30 is equal to 400 times x minus 30. And now we're going to go ahead and solve for x. I'm going to run out of room here a little bit. I wasn't smart with my space. So 300x, 300 times 30 is plus 9,000 is equal to 400x minus 400 times 30 is minus 12,000. And now rearrange this for x. So I'm going to subtract 300 from 300x. And I'm going to add 12,000 so that I'm isolating that x. So I get, those are gone, those are gone. So I get 100x is equal to 9,000 plus 12,000 is 21,000. Divide by 100, and I'm left with x is equal to 21,000 divided by 100 is 210. So now I've solved this equation, but I want to make sure that I answered the question very clearly, which is to say, what is the speed of the airplane in no wind? And I'm going to do what I try not to do, and I'm going to write my answer up here. I'm just being very clear about it. The speed in no wind x is 210 kilometers per hour. And it must be kilometers per hour because it's got to have the units of the other values that we were using in this problem. So if we were using kilometers per hour for other speeds and kilometers for distances and hours for times, then my units must be kilometers per hour. So that's an example of solving one of these speed problems by setting up a rational equation and then solving that equation. We have one more motion example. Jessi trained for 3 hours on Saturday. She ran 8 kilometers and then biked 24 kilometers. And we're told that her biking speed is 4 kilometers per hour faster than her running speed. So we want to know, what is her running speed? Whenever I see the question that's, that we're trying to answer, I go there first to get the variable. So what is her running speed? I'm going to call that x, our unknown. I think that's always a good idea. Figure out your unknown, what you're being asked to solve, and get your variable from there. So after that, let's start looking at these other values that we have. One thing I noticed is that we have her biking speed is 4 kilometers per hour faster than her running speed. So right away, I'm going to say, well, if her running speed is x, then her biking speed is x plus 4. Then we also have a couple of other values, like her running is 8 kilometers, so that's going to be grouped up with her running speed, and her biking distance is 24 kilometers, so that's going to get grouped up with her biking speed. Lastly, we have time. So we're told that she trains for 3 hours, but that's 3 hours total. So we don't have the individual breakdown of, she ran for this amount of time and biked for this amount of time, just that combined, they were 3 hours together. So where are our equations going to come from? Where is this equation going to come from? We have to think about our speed, distance, time. So speed is equal to distance over time formula, and decide what variable is going to link all of these together. And really, the key is in this 3 hours thing. This is the link because this is the combined time of her two activities. So these two activities are going to be linked through the time that they take. So rearranging this equation for time, we have time is equal to distance over speed. And we can say that the time that she spent running plus the time that she spent biking, time bike, is equal to 3 hours. So it's that 3 hour time, total time that's tying these two values together. And now, just like that last problem, we're going to replace time with distance over speed, since that's where all of our knowns are. Here's our distance for running. We have a value. Here is our distance for biking. We have a value. And we also have our variables tied up in the speed. So let's get time out of there, and let's bring in some values we know and variables we want to find out. So to start with, the time to run is the distance to run over the speed that Jessi ran at. Plus we're adding, same thing, we're going to split apart that time to bike into the distance divided by the speed. And all of that added together is 3. So now the distance that Jessi ran was 8 kilometers, and the speed she ran was x. And the distance she biked was 24 kilometers, and the speed she ran was x plus 4. And all of that is equal to 3. Now we've reached the point where we just have our rational equation that we have to solve. Ignoring all the other words and circumstances, this is just a rational equation of the type that we've learned how to solve in this unit. So to solve this, we're going to multiply each side by whatever we have to multiply by to eliminate the denominator. So in this case, we have to multiply by x times x plus 4 to eliminate the denominator. So I'm going to multiply that in to both terms on the left-hand side. So the x's cancel on that first term, so I'm left with 8 times x plus 4. And the x plus 4's cancel when I multiply it over to the second term, so I get plus 24x. And on the right-hand side, I just have 3x times x plus 4. So now I'll expand and start rearranging. So 8x plus 32, multiplying that in there, plus 24x is equal to, and now I'll multiply the 3x into each one, would be 3x squared plus 12x. Now I can see that this is going to be a quadratic equation. I'm going to have to factor to solve it because of that x squared term. So let's move everything over to the right-hand side. So I'm going to subtract away 8x, subtract away 24x, subtract away 32, and I do that on each side of the equation. So minus 8x, minus 24x, minus 32. Gets rid of everything on that side. So I'm left with 3x squared. 12 minus 8 minus 24 is negative 20x minus 32. And here's my quadratic equation that I'm going to have to solve to answer this problem. So I'm just going to make myself some room and start working on the right here. So I have 3x squared minus 20 minus 20x minus 32 is equal to 0. And this is a messy trinomial. So I'm going to need two numbers that multiply to 3 times negative 32. That's negative 96. And they have to add to negative 20. So I find that 8 times 12 is equal to 96, but they would both have to be negative to get me to negative 20, and only one of them can be negative. So that combo is not going to work. But then I tried another one and I found 4 times 24. Those will multiply to 96. So if I make 24 negative and 4 positive, they multiply to negative 96 and they add to negative 20. So that would be 3x squared plus 4x minus 24x. Now I'm just factoring my messy trinomial, just like we were doing way back when we were concentrating on our trinomials. And 32 times x each can be divided by 8. 24 and 32 each can be divided by 8. So I'm going to take away negative 8 times 3x plus 4 equals 0. And that means I have 3x plus 4 times x minus 8 equals 0. So I have two binomials. Each is going to provide me with a solution. So this would be 3x plus 4 equals 0, which means 3x equals negative 4, which means x equals negative 4 over 3 kilometers per hour. That would be the running speed, or x minus 8 equals 0, so x equals 8. Well, what am I going to do about this? I'm going to reject my negative solution. Reject. Because it doesn't make sense to have a negative running speed. So my only answer that makes sense is x equals 8, which means Jessi's running speed is 8 kilometers per hour. And I've solved my problem. So I actually had two solutions to this one. I had to reject one because it wasn't reasonable. So I took a lot of time in this example. As you become comfortable, you're going to find that it goes much, much faster because I was showing you all those steps and trying to explain my thinking in detail. But try some of these problems for yourself and you'll start to get a feel for combining the speed, distance, time formulas together.